And welcome back to experiment number 3, the photoresistor, or more commonly known as light dependent resistor. Right, so this is our building block for today's experiment number 3. And so what are we going to do? We have a transistor block that will switch on when VBE, or the voltage at the base, is 0.6 of a volt for a silicon transistor or thereabouts. We have a light dependent resistor whose resistance varies between just around 1k with the light on it to 120k and above with the light not on it, in darkness, up to a meg or a couple of megs if it's dark. And we have a few resistors, we have a few scattered resistors that we can use. And so that's our starting point. So let's look at what happens if the resistance falls when light is on it and we want the transistor not to switch on. Then we really want to pull the base down. So this wants to be in control of the base, so it wants to pull it down. So we'll plug that into the base. Let's just plug it a bit, one down a bit, so that into the base, and we want to be able to connect 0 volts to it, so we'll plug that in there. And then we want a pull up or something, so it nearly wants to pull that down to below 0.6 of a volt. That's the common voltage, as I said, for a transistor to start conducting. If we stay below that, it won't be on. If we go above that, it will go up to about 0.7 of a volt, where the transistor will be fully saturated. The VCE voltage will be very low and the LED will be at its fullest brightness. But when the light comes away from the LDR and its resistance increases, then we need something here to pull the base up. So normally we'd have something, say, about 10 times the value. So if that's about 1k with the light falling on it, then we want something of about 10k. So I look through my pile of resistors. So we plug the 10k into the board, or into our circuit. We need 5 volts, so we'll put 5 volts on there. We need 5 volts onto the pull-up resistor. We need 0 volts down here, and we also need 0 volts over there. So there's our circuit, and I'll bring up here what the circuit looks like. Well, I hope you can all see it. Here's the circuit, and there's the LDR, or the photoresistor, and there's the 10k. And as I said, the LDR here, it had a light resistance of about 1k and a dark resistance of 120k or more. They're subjective values because it just depends on how much light, where the light's coming from, and what the frequency of the light is, as the LDRs can be frequency sensitive to the light, or wavelength sensitive, and they've also a little bit slow. They don't switch as fast, and you may find them used with a light bulb controlling audio gain, as they give a smoother response because of the slight lag of how it changes resistance to light. So let's put the power on and see what happens. on comes the power. Why is that? Maybe we need some more light. Right, so a bit more light and we're okay. So bring a bit of shadow in and we can see that it is actually lighting up as expected. So we'll have a look at some of the voltages here. Turn that on. Right, so what are the voltages that are in interest? So let's look at the voltage on the base. And there we have about 0.3 volts, 0.35 volts on the base. So if we think about it, we have 5 volts on here. We have 10k there. We have whatever the resistance is of the photo cell, or the photoresistor, and we have a 10k here. Now that's like a reverse biased diode junction, so there's no real current going to flow out of that, only into it, but it only starts to flow in when the voltage between the base and the emitter goes above 0.5 or 6 volts, then current will start to flow. So at this point we can probably treat the base as being a high impedance and that 10k going nowhere. So effectively this current path down here is the 10k plus whatever current is going through there and whatever. So we've got 5 volts up here. The current path down here is through the 10k and through the LDR. Now if we know that the voltage between here and there is 5 volts minus 0.358, we can calculate the current through the 10k. So let's start here. 5 volts minus the 0.366, as roughly it is now, that gives us 4.6 volts across the 10k. So if we say 4.6 volts divided by 10k, that gives us 463 microamps flowing down here. Now 460 microamps flowing down here with a voltage of 0.366. If we divide the 0.366 by the current, that will give us the effective resistance at this point, at this light level, and that comes to 789 ohms. So from this we know the light falling on here is causing the LDR to give us a resistance of 789 ohms, and that is pulling the base down, so no light. So we could, as you can see, it's quite sensitive, just bringing the shadow in and its voltage is starting to go up. So when that gets to sort of around 0.6, you can just see the light, the diode. You can't really see it, I think. You just see it starting to glow. You know, it's just starting to glow down there when you get to around 0.6 of a volt. So then we can work out what the resistance is needed when it's about 0.6 of a volt. Because if it's at 0.6 of a volt here and 0.6 of a volt there, then the current's not going to be very much down here, so we can take it that most of it is still going down here, the little bits going this way. So then we can say, well, it's 5 volts minus 0.6, which is 4.4. Divide that by the 10k. That will give us the current flowing through it. So the current is 440 microamps. And so if you want to know what the resistance is here again, we can do it again by going 0.6 divided by the 460 microamps. And it's now increased to 1363 ohms. So from the currents and the voltages we can calculate the effective resistances and that. And then when it goes right up and lights up, You can see we're going up to fully dark. Let's shield it as much as we can. So we're up to 2.5 volts. So again, we can look at we can see what the resistance was of the sensor. Then we can do 5 minus, well, it's 2.5 volts, isn't it? 2.5 volts divided by 10k. It's got 250 microamps. Which, without thinking about it, you should know it, shouldn't you? That if that's if there's 2.5 volts dropped across the 10k resistor, there must be 2.5 volts dropped across the LDR, and the current must be the same. So it must be at that point in time has a resistance of about 10k. So I don't know why I was bothering working it out. That's one that should have jumped out and bitten you on the bum. But there you go. That's how you can put an LDR or a light sensitive resistor, a light dependent resistor, or a photoresistor. There's lots of names for them, but that's how you can do it so that it will light the light when dark falls on it. So I hope you like this. You don't find it too boring, and if you want to see more, subscribe, and I'll catch you on experiment number 4.